Good morning, everyone. If anybody has any questions, feel free to just blast it out. A lot of this presentation is from the American Galvanizing Association, a non-for-profit since 1933. Did you know that 25 to 30% of corrosion can be eliminated if the right corrosion protection system was installed right out of the get-go? Here's guide rail. I don't care if you're federal, highway, state, county engineers. It seems like all the guide rail throughout the United States is hot-dip galvanized, but we paint our bridges. I'm from Chicago, so I'm just going to show you one railroad bridge from Chicago here in a little bit. Here's a piece of rail. Because the corrosion protection system paint was not maintained, you have an ultimate failure plus a safety concern. What about this? Can you fix this? How would you fix this? You can fix it. How would you fix it? Blast it and repaint it. Make sure you remediate the salts, though, before you do that. But that can be fixed. What about that? This is an old railroad bridge. They probably got about 80, 90 years out of this bridge. This is on Damon Avenue, about a mile south of the United Center. Can you fix that? A lot of people say you can't fix that. Well, how would you like to go under this bridge? Does this bridge seem safe to anybody? Anybody have a concern with this? They fixed this bridge about 2 years ago, and this is what they did. You can see they come in. This is one thing that's nice about steel. They came in, they cut the old steel out, put new steel in. But my concern is, they did this a little over 2 years ago, and today they still haven't put a barrier on it. And the reason why, if you don't put a barrier on it, what's going to happen? You're going to have the same results. You can see some cross braces on the other side of the bridge. That's the cross braces on the other side of the bridge. They're just starting to repair those, but still they're fixing the steel, but not putting paint on it. If they put a paint on it to put the barrier on there, you wouldn't have that problem. I got this picture from Rich. He told me, it's kind of a fuzzy picture, but this is actually a bridge that was hot dip galvanized in 1969. It's in Connecticut, and it's still in pristine shape. They spent $0 to maintain it. I show you this bridge because I believe this is a world famous bridge. And the reason why I say that, in 1969, the state of Indiana, this is north of Indianapolis, in the snow belt where they use salts and things like that, they hot dip galvanized the two northbound lanes of I-69. The two southbound lanes, you can see there's the old green lead-based paint. They did that in 1969. In 1984, they needed to repaint the bridge. They came in, they blasted the paint off, repainted it. Galvanized side was still fine. In 2002, they decided to widen the bridge. You can see the air gap between there. So when they decided to widen the bridge, they put 4 new beams in there. They looked at the galvanized side. They said, man, this galvanized sides hold up pretty good. So they did their due diligence, and they came out and they said, you know what, we're going to metallize these other pieces. So here's the bridge today. I've been doing a case study on this bridge since 2011. Here's the underside of the bridge. The DOT has spent $0 to maintain the galvanized side. Does anybody want to take a guess how many mills is still on the galvanized side today? No takers. Two mills. If you come out with, for a new bridge, how many mills on a 2-part paint system do you put on? 6, 8, 10? How much? 12 to 16? Okay, well here's a bridge that's been in salt-infested environment for over 45 years, and you have an average of 6.82 mills. The question I always get, well Kevin, that's after 45 years. What was it when it was put up? We're trying to get that information. Rob Connor from Purdue is trying to get that information from the Indiana DOT because it's on microfilm and it's way down deep. But after 45 years, we have still 6.82 mills. This is just a few bridges in Chicago. I don't know if anybody was at the New York Bridge Conference, but AECOM and the design engineers did a presentation on it, and they said that the circle interchange in Chicago is one of the most difficult projects that's going on in the United States today because they've got the tunnels underneath, and what they've done is they're actually redoing the whole circle interchange, and they're galvanizing and metallizing all those pieces. Anything that's too big to be galvanized, they're metallizing. Anything that can fit in the bath, they're hot dip galvanizing. In the last 5 years, they've galvanized over 72 million pounds of bridge beams. This is the old Tappen Zee Bridge. And the old Tappen Zee Bridge, the New York Thruway, what they were doing is these bottom beams that this goes back about 7, 8 years ago. I know they're replacing the bridge now. But they wanted to replace those beams because it was totally rusting out, and they only had 5 hours to take the old beams in and put the new beams in. The New York Thruway gave MC Ironwork the job, and MC Ironworks came back to the New York Thruway and said, hey, listen, you know what? We can do the bridge and no problem, but the biggest problem we're having is the timing. You want us to finish this bridge up in 6 months? Because of the 3-part paint system, and they have a brand new paint facility, they couldn't get it done in time. New York Thruway says, you know what, just figure out a way. They decided to galvanize those pieces. They didn't look at life cycle costs, they didn't look at upfront costs, they looked at, hey, you can get new pieces in, you can finish it up on time. MC Ironworks finished that bridge up 2.5 weeks early, and they saved the New York Thruway over $2 million by galvanizing over paint. See, most folks think that galvanizing is here and paint is here. It's not like that anymore. I mean, here's a case study. You can actually go back and you can see in history that galvanizing was less expensive than the paint system. The law of entropy, what happens when steel gets exposed? It wants to go back to its more natural state, ore. And the definition of corrosion, I just want to point out, it's an electrical chemical reaction. Solution, long-lasting zinc protection. It's one of the only coatings that's going to give you a barrier, it's going to give you cathodic protection, it's going to form a zinc patina, and it's going to have a metallurgical bond to the steel. Here's a bridge. As long as the paint, the metallizing, or the galvanizing stays intact, will that bridge rust? No, the barrier is doing what it's supposed to do. It's protecting the steel. If something is hot-dip galvanized, it actually has cathodic protection. What do we mean by that? The zinc will actually self-sacrifice itself over and cover up the scratch. That's a big attribute of hot-dip galvanizing. Why is that? It's a law of nature. Because zinc is the anode, steel is the cathode, the one on top is always going to want to protect the one on the bottom. Another interesting attribute of hot-dip galvanizing, has anybody been to a hot-dip galvanizing plant here? A few of you? Okay, well, basically what happens is a piece of steel goes down into the molten zinc, and when it comes up out of the molten zinc, the first thing that hits it is the air. Once the air hits it, within the first 48 hours, the first patina is formed, zinc oxide. It sits around a little while. Whether it gets rained on or there's moisture in the air, the next patina form is zinc hydroxide. Sits around a little while longer. By the time the carbon dioxide gets finished with it, this is usually 12 to 14 months, the last patina form is zinc carbonate. Zinc carbonate corrodes 1/30 of what steel corrodes at, so it's going to slowly sacrifice itself, but it's very slowly. Has anybody ever heard of a problem of painting over galvanized steel? Yeah, the problem is you can't paint over the zinc oxide or zinc hydroxide. There's a spec, ASTM D6386. If anybody wants a presentation, a full on that, we can talk about that. But this is how zinc protects itself. Another interesting attribute of hot-dip galvanizing is it's metallurgically bonded to the steel. What do I mean by that? You've got 75% zinc and 25% iron, so it's part of the steel. These intermetallics of iron and zinc. The next is your gamma, which is 9010. Your zeta is 94.6, and your last is your 100% pure zinc. You don't have to worry about moisture coming underneath the coating and popping and peeling it off. It's part of the steel. If I took a Band-Aid and put a Band-Aid on the back of my hand, that's like metallizing or paint. It's a mechanical bond. Hot-dip galvanizing is like your skin. It's actually part of the steel. So you're not going to pop or peel or chip it off. Take a look at the hardness of hot-dip galvanizing. The diamond pyramid number of steel is 159 DPN. The hardness of the gamma is 250, the delta is 245, and the zeta is 179. So the first three coatings of something that's galvanized is actually harder than the steel itself. The zeta is 70, it's soft, so you might dent it. That's why I can take pieces of galvanized steel, you can beat on these, even on the sharp edge, and it's not going to pop or peel off. Edges. Because we grow the coating and then freeze it, this sharp edge has the same amount of zinc as this flat surface. And anytime you paint or metallize, you have a human error in there. With hot-dip galvanizing, it's a dip process, so it's more of a uniform coating because we go down in the zinc and then we come out. And for you who haven't been to a galvanizing plant, this is what happens at a galvanizing plant. Steel comes in on a truck or a bike. Goes into a pre-inspection area, okay? Any tubular products needs holes in it because we're doing the inside and the outside. We got to get the air out and the zinc in. Gets degreased. We got to get rid of the grease, grime, oil, or dirt. If there's any impurities on the steel, zinc won't stick to it. After it gets degreased, it goes into a pickling bath. We need to get any mill scale or any oxides off the steel. Once the steel is totally clean, what's the first thing that steel is going to want to do? Yeah, it's going on our rust oxide because it's totally clean, it's moist. So we come out of the pickling bath, we go into a flux bath. The flux bath does three things. It preheats the steel to 160 degrees, puts a light coating on the steel to keep it from oxidizing, and it helps the zinc flow a little better. After it comes out of the flux bath, it goes into a zinc bath. Most zinc baths are, in America, we heat them to anywhere between 830 and 840 F. To meet the ASTM 123 spec, we have to have a minimum of 98% pure zinc in our kettle. And you have this iron diffusion process where you've got the iron coming out and the zinc going in, so that's it's part of the steel. And this just shows you what a galvanizing plant is. It's an overview. You got your pre-inspection. Your first tank is your degreasing. You have some pickle and rinse tanks. Your flux tank is there. There's your molten zinc bath, and that's just a quench tank to cool it so the guys can work on it after it comes out of the bath. Hot dip galvanizing is a factory controlled process. We do the same thing day in and day out. Temperature doesn't bother us. Moisture doesn't bother us. Humidity doesn't bother us. After it comes out, what you do is you just take a mill gauge, dry film thickness gauge, and just check to make sure you meet the millage on there. If there's any impurities on the steel, when you come out, you're going to see it right away. Here's a charge of beams that one of our guys in the back missed. There was some mill writing on there, and it was in the center of the bundle, so our guys at the kettle didn't see it. Otherwise, they would have ground it off. But this is 10 minutes out of the kettle. You can see any impurities on the steel, zinc won't stick. So we know instantly whether the zinc is good or bad. We don't have to wait a month, 6 months. We know the minute it gets pulled out. And if you have to fix that, you can do a 780 repair, or you can regalvanize it. We do stuff in various sizes and shapes. We're recyclable. That's big today. We have a whole presentation on the sustainability of hot dip galvanizing. No volatile organic components. And this is actually a life predictor where academia and a couple associations got together and said, how long is hot dip galvanizing going to last in these different environments? So if you give me a piece of steel to galvanize today, I got to give you 3.9 mils. That's the spec. If it's under 3.9, it doesn't meet the spec. So if you're in a suburban area like that bridge in Indiana, at 3.9 mils, you're going to get about 95 years. You know, some people say, well, you know what, metallizing lasts longer than hot dip galvanizing, and metallizing is a great coating because we're going to put it on 10 mils. The thing is, when we galvanize something, we have to wait for this piece of steel to heat up to temperature. So we don't put on 3.9. You can see in that bridge in Indiana, after 45 years, we still have almost 7 mils still on there. The big question is, what was it when it started? So so we got a bridge that's 45 years old. It still has over 6 mils of zinc. So if you go out to the chart here, we're off the chart here, and we're off the chart there. Federal Highway says they're looking for a 100-year bridge. Well, we've got some out there. There's over 100 bridges that were galvanized in the 60s, and none of them, to my knowledge, have needed any maintenance so far. Remember, hot dip galvanizing is metallurgically bonded to the steel, and hot dip galvanizing has cathodic protection. Other coatings, I'm going to talk a little about metallizing because some folks don't know what metallizing is. So here's metallizing. You can see the chart here. You can see so it's either zinc wire or zinc powder. Okay, it's either shop or field applied. That's one of the advantages. It can be field applied. And one of the repair methods for repairing hot dip galvanizing is metallizing. It's 85% less dense than hot dip galvanizing, and it's a mechanical bond, not a metallurgical bond, so you have no alloy layers. And so what you have, this is for like zinc powder, so it gets heated up, and then it gets atomized at the gun, and then it gets sprayed on with air. You got to make sure you have a good profile, though. If you don't have a good profile, it's not going to work. This is the twin arc. Most of the bridges are done with the twin arc because it's a much faster. We have 2 wires, a positive and negative, and as they touch, it atomizes the zinc, and then they have some an air that actually blows it onto the steel. Here's the inside of the gun, so you can see the air nozzles. There's where the zinc wire is, and this is just, I put so you can see where the wire touches, and then that's where you get the atomization once it. These are just some beams that were actually metallized at a shop, and some cross frames. One of the things about cross frames, there's a lot of waste on cross frames, so a lot of the DOTs are starting on all the smaller pieces. They're galvanizing them because it's actually a little less money. For metallizing, you have to make sure you have an SP5, SP10 blast, and you have to have an angular profile. If you don't have an angular profile, you're missing the boat. Another thing, you have to have at least a 3 mil profile also. So this way you get the good adhesion. You don't want to use round shot. Here's just a gentleman that's actually, you can see him, that's what metallizing looks like. And this is, I wanted to get to some of these bridges and actually do some mill readings to give you folks, but unfortunately I wasn't able to get there. But this is actually in New Jersey. And then this is one this is the Ridge Avenue Bridge in Philadelphia. It was actually galvanized, metallized in the 30s. And there's still some evidences of some zinc still on that bridge. And this is the Memorial Bridge. This is this is a very unique bridge. This bridge was all metallized, and this is another thing I thought was pretty interesting. Take a look at these cold bent flanges. There isn't a bridge in the world that has done this. The first one. I thought that was pretty unique, and they were able to do that with metallizing. So I think this is going to be a world famous bridge also because of that. This is actually a case study that Federal Highway did in Illinois where they have paint and metallizing going head to head. They actually did this in 1991. The paint is holding up very well and the metallizing is holding up very well. So the verdict isn't out on that, but it's nice we got two that are doing the same thing. This is the underside of the metallized on that bridge. And here's the Whittier Bridge. This bridge actually used hot dip galvanizing and metallizing on this bridge. So a lot of the folks are starting to do that because with galvanizing we're limited to weight and length. So on things like that, they're metallizing the bigger pieces, and anything that fits in the bath, they're galvanizing them. And here's metallizing service life. A lot of people says, well, metallizing is it's a great coating, but I got this from an association. And this is what they say. That's why a lot of times the DOTs, what they're doing when they metallize something, they're coming in and either putting a clear sealant on it or a paint to give it the synergistic effect, which is the life of both coatings times 1.5. So here's your other coating. Here's your metallizing. You can see it's less dense. You see, it's not metallurgically bonded, but it's a very excellent coating. You got your hot dip galvanizing, which is a metallurgical bond, which is a dip process. Then you got your zinc-rich paint, which isn't metallurgically bonded, which is either sprayed on or brushed on. Then you got your galvanized sheet, your G60, your G90. Some of your young folks, I'm going to mention two names. You won't know who they are, but a lot of you old folks like me, you'll remember. Z-Bar, Rusty Jones, where are they today? They're gone because the auto industry is starting using galvanized sheets. So it shows that zinc works. And then electroplate. Design and fabrication, just to go through, we're the liaison between the design engineer and the fabricator. Oversized pieces, this is where, for bridge pieces, this kettle was only 8 foot deep, that was actually 10 foot, it's called a progressive dip. We came in, dipped 3/4 of it, we flipped it over, did the other quarter. Same thing with these big bridge beams. We come in, we do 3/4, flip it over, and then we do the other half. This is a 72 foot piece. You can see they're getting ready to flip it over and do the other half. And you can see this progressive dip mark. This is actually in Chicago. People say, well, what about that? Remember, hot dip galvanized is metallurgically bonded. You don't have to worry about the adhesion in this progressive dip mark. We overlap at about 2 inches. So if you put a mill gauge here and a mill gauge there, you probably get anywhere between 9 to 11 mils. You put it in that progressive dip mark, there's about 13 or 14. Here's in the Truss Bridge, same thing, we're progressive dipping it. Standards and inspections, this is pretty important for you bridge folks because you want to spec the ASTM 123, ASTM 153 for your hardware, small pieces and things like that. And then the ASTM D385. A lot of people don't want to talk about this, but people say, hey Kevin, this is going to a trade show, I want you to galvanize the 385. ASTM 385 is not for the galvanizer, it's for the fabricator, okay? This is your typical iron zinc alloy layer. It's not a very good picture. What happens when you have reactive steel, okay, you have this irregular iron zinc alloy layers and you got these columnar crystals that are growing more vertically. So at 3% silicon, you can see the columnar crystals. At 10, look at the columnar crystals at 0.24, 0.44. How much adhesion do you think you have here? You're not going to have a lot of adhesion here. That's why in the spec, if you're doing bridge pieces, most of those bridge pieces are, and the mills can give you bridge beams that have the silicon level that are correct, but it's going to cost you more money and you're going to have to wait on it. So what we've done in our spec with Illinois and a lot of DOTs, we're making sure that they sandblast the steel before it comes to the galvanizer. By sandblasting the steel, you're profiling it, and by profiling, instead of those columnar crystals going straight up, they're actually going to grow into one another. another. So you're not going to get that rapid growth rate. Because when you get something like that and you hit it or you ding it, you can chip off most of the zinc. You're only going to have like a mil or a mil and a half in there, and obviously you don't want that. You can do repair on that, but you can mitigate that by blasting the steel before it goes to the galvanizer. And this is what some of it looks like. If you have high reactive steel with silicon or phosphate, I mean, it came in nice and smooth, but that was after galvanized. Here's another piece. You can see the piece together. Remember, we're just putting this in molten zinc and coming up. We didn't do anything different. It's steel chemistry. See how nice and smooth that is? Look how rough that is. So if this was blasted, before it was galvanized, it wouldn't look near as bad as that. I'm not saying galvanizing is perfect, because you have a pH of 3.5 or less, or a pH over 13, that's not the best choice. We'd say galvanize the steel to protect the steel, and then paint over the galvanize. And this is some real world applications. Stearns Bayou Bridge, it's the oldest bridge in America that we know was galvanized. 1966, and everything on the bridge was galvanized. Here's the bridge itself. I did a case study last year. This still has over 5.5 mils on it. This is the underside of the bridge, which is going to be the thicker steel. There's some handrails on the top side of the bridge, okay? You know, anybody know what that is? Pigeon droppings. Pigeon droppings doesn't bother hot dip galvanized. Here's the rails up on top. Now you'll say, well, Kevin, it looks like the galvanizing is gone here. Remember, the thicker the galvanized coating, the longer the galvanizing is going to last. These are rails, it's thinner, so these probably maybe only had 5 or 6 mils when they were installed. Okay, but these haven't failed. You also have snow plow and trucks coming through that's taking salt and ice and stuff over there. So you're going to have more wear there. But take a look. Here's my mil gauge. You still have almost 3 mils of zinc on there. The ADA layer, the 100% zinc layer, is gone. This is the time to come in and paint in probably a year or two, okay? The problem is the DOT missed their window to, when you paint this, all you have to do is come in and power wash and paint it. Do you know that there's trillions of pounds of hot dip galvanized steel out there that needs maintenance like this? And now it's the time to come in and power wash and paint it. If you wait till it gets like that, some of these, there's about 5 spots on these rails, you're totally down to the substrate. There's no zinc there. So now you've got to hand tool or hand clean that and then paint it. So what you want to do is you want to paint it, which is in this stage, so you don't have to sandblast, you don't have to come in and grind. You can just power wash it, make sure there's no salts on there, power wash it, and then give it a coat of paint. You're done. This is just another bridge out here in the Northeast, Maryland, hot dip galvanized. Most of these were done in the late 60s, early 70s. PA, New York. If you're a design engineer, what do you want on your resume? That you spec that or you spec that? I mean, hot dip galvanizing and metallizing is really coming on strong. We have to do something different, because if we continue to do what we've done, we're not going to have the money to maintain our other stuff. So we have to get 50, 60, 70 years out of the new bridges we're putting up without having to do any maintenance, so we can continue to work on our older bridges. Questions? Clear as mud. If anybody wants a presentation, this is a short presentation. I rushed through this. I only had 20 minutes. We can come out to your plant, do a lunch and learn. You get CEU credits. Question?
What are the typical bed length for beams? What's the longest beam?
In this area, probably about 85 feet, but it's also going to be dependent on how tall the beam is. Okay. I'll be back in the back if anybody has any questions. Thank you.